So we looked at right angle triangle trig, but obviously angles are bigger than 90 degrees. How do we handle angles of any magnitude? There's our number plane. I'm just going to draw in, there it is, our unit circle. Interestingly, I always find this strange, because when we do bearings, we usually start at north and go clockwise. But then when it comes to doing angles of any magnitude, we start at east, if you like, and we go anti-clockwise. Anyway, that's how we do it. We obviously have 4 quadrants, we know that. What we want to do is get everything in terms of right angle triangle trig. So we draw in right angle triangles in each of the 4 quadrants. And it's like a butterfly, if you like. It creates a butterfly. And that way we want to get it with reference to that acute angle in each of the quadrants. So in the first quadrant, everything's normal because it is a right angle triangle. The angles go between 0 and 90 degrees. We don't have an issue. The second quadrant is what I call the 180 minus theta. Basically the acute angle is theta. So we work with 180 degrees minus theta. That would be the equivalent angle that would get to that point. What we look at then is we see that if this is our number plane, the x coordinate would be negative, the y coordinate would be positive. The hypotenuse we're thinking of as a distance, and it's always positive. So the sine ratio would be positive over positive. It still gives a positive number. Cosine ratio would end up giving a negative number because we'd have a negative divided by a positive. And the tan ratio would also give a negative result. In the third quadrant, it then becomes 180 plus the acute angle. The sine now turns out to be negative, cosine's also negative, and the tan ends up being positive, which brings us to the fourth quadrant, which would be going 360 degrees, but then take away the acute angle. Sine's negative, cosine's positive, tan's negative. It then allows us to do trig any size angle we like. So if I wanted to work out the sine of 260 degrees, and before fancy calculators, you used to have a table of values, but it only went from 0 to 90 degrees, so you had to convert everything. And if you wanted to work out the sine of 260, you'd say, oh, okay, well, which quadrant's that in? 260 would be in my third quadrant, so I know it's negative. And then what would the equivalent acute angle be? I said, well, the third quadrant is 180 plus theta. Well, 180 plus 80 would give me 260. And so then I could look up a table of values. What's the sine of 80? And it'll be the negative of that. Turns out to be negative 0.9848. Fortunately, you now have calculators and you don't have to go through all that. You can just press the buttons and the answer comes up. So tan 20, same sort of idea. Oh, that's in the third quadrant. But that would be positive. The equivalent acute angle would be 40. Secant, which was the reciprocal of cosine, of course. So cosine 105, that's the second quadrant. It's negative, equivalent to an acute angle of 75 degrees. 430, well, if we go bigger than 360, we just are going round and round and round in circles. Now all I've got to do is keep subtracting 360. And in this case, when I do that, I get an acute angle straight away, 70 degrees. Tan, now this one's quite interesting. Tan of negative 67. Negative means go back the other way. So instead of going around anti-clockwise, let's go around clockwise, which would be the same as going around 293. Tan is negative and the acute angle is 67. Interesting, because tan ends up being an odd function. And that satisfies our rule for an odd function. Function negative x is equal to the negative of function x. Here's a question then. So there's the point P, it's sitting on our circle. This time the radius is 5. We want to find coordinates for that point. Now, I can create a right angle triangle there, and I can very easily use trig to work out 5 times cos 30, that's 5 root 3 on 2, and the y value would be 5 on 2. There's my coordinates. But what happens at the boundaries, the points that aren't actually in one of the quadrants, on the boundary of the quadrant? What happens there? So there's our unit circle with those values put in. What I do is I create this fictitious triangle, and I say, well, look, I'm going to make that angle equal to 0. It's a right angle triangle. I know the angle sum of a triangle is 180, therefore the other angle must be 90 degrees. Now, its length there is 1. But hang on, if that angle's 0, I haven't actually lifted anything, so that side must be 0. And then by Pythagoras' theorem, I can work out the hypotenuse is 1 as well. So now if I want to work out the sine of 0, I can just read off my triangle. Oh, it's 0, cos of 0 is 1, and the tan of 0 is 0. I can also read off 90 degrees. Tan becomes interesting, of course, because we get 1 over 0. Tan is undefined at 90. On the graph, you end up with a vertical asymptote. 180, oh, which quadrant am I in? Second or third? Well, I could choose either one. It doesn't really matter. And then I'd say I said it was in the second quadrant. I'd say, well, sine in the second quadrant's positive. It would be the same as an acute angle of 0. Oh, well, sine 0 was 0 anyway. Cosine in the second quadrant's negative. It's also negative in the third, so it didn't really matter. I get negative 1, and I can do a similar thing for 270. Reality with the boundary values, again, just punch it in the calculator and it tells me what they are, but if you don't remember them. So plotting the basic graphs then. And all I really do is plot the boundary values. They're the key points when I'm drawing trig graphs. Now I'll do sine first of all. I know it goes up to 1 and down to -1. And the key points every 90 degrees, and maybe I got a bit carried away, but I went all the way up to 720 and back the other way to negative 360. I think, well, where do I start my curve? I know the sine of 0 is 0. Then at 90 degrees it's 1, and I know that pattern just keeps repeating, so I go down and up, down and up. And I just draw a nice smooth curve, and there's y equals sine x. So looking at that, what can we see? Well, the domain is all real x. There's no breaks in that curve whatsoever. The range, it goes in between -1 and 1. With trig graphs, we have a thing called period. The period is simply how long until it repeats. But it has to repeat precisely. So I couldn't just look at, say, 0, oh look, it's back at 0 at 180, and think, oh, the period's 180. It hasn't repeated precisely, because at 0 it's going up, it's increasing, but at 180 it's decreasing. It's not until we get to 360 that it's repeating precisely, it's going back up again. So it takes 360 degrees for the sine curve to repeat. Alright, what else can we tell? Well, let's look at the picture itself. It has rotational symmetry there. So I know it's an odd function. That means the sine of negative x will always be the negative of sine of x. That could be a useful property. Let's do cosine. So same deal, let's plot the key things in. Cosine of 0, that started up at 1. Then at 90 degrees we went down to 0. That pattern repeats, and we put the curve in. Now it's no coincidence we've basically got the same curve, but we've got a horizontal shift. Well, that makes sense, because sine and cosine are complementary ratios, and we said the two angles add up to 90. So really, cosine of x, I could have said, hey, let's draw the graph of sine pi on 2 minus x. So we would have a shift of 90 degrees, or pi on 2 radians, but the negative x would also mean, oh, we've got a reflection as well. Hence, we get basically the same graph, but just a shift happening, some sort of translation happening. That therefore means the domain's going to be exactly the same, which it is. The range is going to be exactly the same. The period's going to be exactly the same. However, the symmetry is not exactly the same. If we look at this one, we've got reflection in the y-axis. So cosine is an even function. So the cosine of negative x is actually equal to the cosine of x. Let's do tan. Tan of 0 was 0. We then said 90 was undefined, vertical asymptote, and that pattern repeats. So we get x-intercept asymptote, x-intercept asymptote, and so on all the way along. We know we've got to bend towards the asymptote. We also know the tan curve is positive in the first quadrant, so between 0 and 90, and then it was negative in the next quadrant, positive. We end up with that sort of shape, but repeated between the asymptotes. Now when you draw a tan graph, don't draw it like a cubic. That's one of the mistakes you see. Often the people just draw it like a cubic. The tan graph comes through at 45 degrees. So it always comes through at 45 degrees when you're drawing a tan graph. Domain, a little bit harder to write because of all those asymptotes. So I've said, oh look, it's all real x, except, now obviously I couldn't list them all because there's an infinite number of them going backwards and forwards. So I said, look, I know it starts, the first one's there at 90 degrees, and then every 180 degrees before and after. So I just say, oh well, plus 180k, where k some whole number, some integer, multiple of that. Range would be all real way. The period for this one though is only 180 degrees, not 360 degrees. And if we look at it, yes, it's got rotational symmetry, so it is an odd function. Tan of negative x is the negative tan of x. I'll just do one of the reciprocal graphs, because if it's a reciprocal graph, then really I'm just drawing 1 over, so like we did with reciprocal of any function. So if I want to draw the cosec graph, then I just have to do the reciprocal of the sine graph. So there's my construction. I've dotted in sine. You go, right, I'm going to find the reciprocal of that. So what sort of things did we say? We said the x-intercepts become vertical asymptotes. 1 became a key point, because if you turn 1 upside down you get 1, same with negative 1. Where the original one was increasing, the new one will be decreasing, and vice versa. I've got to bend towards the asymptote, so I end up with a series of U-shapes there between the two asymptotes. That shall do us.